Hopefully that's working. So can you hear me? Okay, great. So, 4 talks, and they aren't just random people that have been dragged in off the street. There's actually a sort of a reason, like a methodology to this madness, and essentially all the talks are connected, and the way they're connected is sort of illustrated by this diagram, so that proves it must be true. And so first you've got me on the left there. I'm going to talk a bit about causal inference. I'll explain what that means in a minute, and a bit of background into the whole causality thing. And I'm going to be followed by Ross and Stephen, who are going to talk about a thing called elicitation and some tools for that, and then Lizzie's going to talk about causal discovery. And the system that we've come up to unite all of these things is all around the question of, do you already have a model, or an idea of like the structure of a model in mind? Because if you don't have a model, but you have some people that know things about the domain you're working in, then you're going to be particularly interested in Ross and Stephen's talk tonight. If you have a lot of data and the model and the system is extremely complicated, then pretty much your only option is going to be to turn to causal discovery. But either way, somehow you're going to come up with a model, and having come up with a model, you can then do causal inference. And some of those methods come up with their own causal inference tools. There's many tools, but I'm just going to talk about one of them tonight, which is called Causal Wizard. And I tried to make this title a bit shorter, but I couldn't remove any of the words, so we're just stuck with that big sandwich there, and hopefully that won't stop us getting to the pub on time. But it's all about helping people, subject matter experts, people who sort of understand a specific domain really well, to get causal insights from the data that they already got, their historical data. So I promised that I'd give you sort of a bit of background into causality and causal inference. And one of the first questions that often comes up is, causality sounds like this incredibly intricate, complicated concept, but it really is quite simple. It's just about cause and effect. And particularly working in data science and machine learning, when we're dealing with systems and infrastructure in the real world, we often get these questions that are inherently causal. So, for example, if somebody comes to you and they say, I've got this problem and I want to understand what would happen if I changed this, or these events occurred, but I don't understand why they occurred. Now, you can use machine learning to approach those kind of problems, but there are some limitations, and particularly most machine learning methods are not explicitly causal, and even when the questions are. So, what's actually different between a sort of causal AI or causal ML model and a sort of conventional associative machine learning model? You can do predictions with an associative model, but I think the real difference is when you are changing something from your data that you have to the system that you want to model, you're going to get better results if you actually sort of explicitly capture the effects of those changes. So, for example, if you're going to intervene in a system, then you really need to consider the causal angle to be able to understand the effects of that intervention. Or if you know that someone else is going to intervene and for that reason the statistics are going to be different, then again, maybe you really need to think about using a causal model. There's this phenomenon, which this guy on Twitter or X or whatever it's called, is he said, he called it Schrodinger's causality. So you remember like Schrodinger's thought experiment about the cat in the box that was simultaneously dead and alive. So people in research, they sort of often talk about, in one part of the paper they may say, doing X reduces the risk of Y, which is a causal statement. And then later on when they get to conclusions, they say, or the methodology they say, this is an associational study, so we can't make any causal conclusions. And they kind of say, don't assume any causality here, this is just association. And so what they're doing is they're kind of sort of simultaneously saying that it's causal and it's not causal, and hence Schrodinger's causal inference. And I just saw on the same website last week, this post about a paper where they looked at people's perceptions of causality when you explicitly say, this is not a causal result, this is just an observational correlational result. And people do draw these causal conclusions anyway. So not only are you kind of sort of hedging your bets about whether this method is causal or not, but people are misled into believing that your study is causal. And so the next point that comes up is, does it matter if you don't deal with causality explicitly? And sometimes, maybe the results are going to be okay, but you literally have no way of knowing that in any given case. And, it's very easy to find correlation and other association in pretty much any random data. This guy, Tyler Vegan, you see his website at the bottom there, he's got a load of hilarious, spurious correlations, which you can enjoy. But, not only can you observe effects that don't really have any meaning in the real world, but you could imagine you could train models that essentially rely on these correlations, and then you disrupt them in the real world, and your models give you terrible results. But there is one part of sort of generally sort of popular science where people do understand that this experiment design does produce a causal conclusion, and that's the randomised controlled trial. And I think it's just worth understanding what's going on there, so that you can see that it's not really anything that special. It's just there's a couple of key things that are happening. So first is randomisation. There's got to be this equal chance of the subjects or the sample participants being assigned to any of the different groups in the experiment. And then there's an intervention which you make to one of the groups only. And because of that randomisation, you can make this conclusion that significant differences between those groups are due to that intervention, and they're not due to some other feature of the original participant pool, because you randomised it when you did that assignment. The problem is that in many cases you can't do a randomised controlled trial, right? Because, so for example, you can't go back in time and change what happened. It may be unethical or infeasible to do a randomised controlled trial, right? You can't give kids cigarettes and tell them to smoke 40 a day for 10 years to see what happens, right? And it's just luck of the dice whether they get the real cigarettes or the lolly ones. So if you can't do a randomised controlled trial, can you still model causality? And the answer is yes. Basically, to do causal AI without a randomised controlled trial, you need two things. You need some data, and you need a causal model. And there's many different types of causal model, and we're going to talk about a few of them tonight. Some of the other speakers are going to cover a lot more sophisticated models. One of the key things about the causal model is you can produce that model, or at least you can get the structure of it from expert domain knowledge. And that creates a really good opportunity, because a lot of organisations, particularly sort of infrastructure, government, industry, they collect a large amount of historical data. So the opportunity is there to make use of that historical data, especially if you've got really good domain knowledge. So, for example, engineers who understand the effects of rain and soil types on pipe network corrosion. If you've got a good idea of that system that's affecting those systems, then you can do a lot of work to answer these sort of causal questions. So here are some of the sort of questions that have come up to sort of across my desk in the past couple of years. So, what is the most cost-effective maintenance treatment for preventing failure events? And so we want to understand, like, not just what events happened and through predict events, but we want to understand what can we do that's most cost-effective in terms of changing the way we manage that infrastructure in order to change the occurrence of those events. And another one that comes up, which has a big dollar value attached to it, is over the past 10 years, what would be the service level result of these different renewal investment scenarios? So if we put in this amount of money into this bucket, what do we get? If we put a different amount of money into a different bucket, what is the network outcome? And we can actually go back in time. If we've got a causal model, we can give you a sort of counterfactual answer about what would have happened if you changed your investment policy. Okay? So these are the kind of causal questions that we can address. So that was the background. And now I'm going to talk a little bit with a little example about a tool, Causal Wizard, which you can use to answer some of these questions. The tool is actually not aimed at really, probably a lot of the people here who probably mostly have AI and ML programming skills, but it's really aimed at people who have strong domain knowledge and data. And another thing I'd like to make is that the tool doesn't contain any secret source. There are no methods or algorithms that are not published in the literature. And it's mostly based on a library that I'd recommend called DoY. So everything you can do in Causal Wizard, you can also do with this Python library called do-why, which I highly recommend. So you remember a couple of slides ago, you saw exactly the same thing, and I said, remember, you've got to have these two things. You've got to have some data, and you've got to have a causal model. So for the example that we're going to work through, we're going to use a data set called the LOND. It's really old, but it's one of the sort of textbook causal inference case studies. And like most sort of non-time series causal data sets, it's essentially tabular, right? So you've got a big table, rows of your samples. So these are a bunch of people who undertook a training program or didn't. Either they did or they didn't. And what they were interested in was, does this training program improve their wage 3 years down the track? So they want to understand, does this training program provide a benefit to those people? And they had a bunch of variables of factors that they captured about those people, and they sort of tracked what happened. So in addition to that data, we're also going to need to provide a structure of a model. And really this is capturing that domain knowledge that I said you'd need to provide. And specifically in this tool, in Causal Wizard, we're going to capture it as a DAG, which is directed acyclic graph, directed edges arrows and acyclic, there are no loops. We need to include at least the treatment and the outcome. You can think of that as like the cause and the effect, right? You've got to have the cause and effect to model that thing. And then we also have this sort of overall aim that we want to include all these relevant direct causal relationships. And I think in some of the later talks we're going to sort of talk about how to sort of get people to understand and map out what those relationships might be. We're just going to get straight to it. So the most basic version, you've got your treatment and outcome. The treatment in this case is, did the subject receive that training course? And then the outcome is what happened to their wage 3 years later. You can see how old this example is, 1978. And then we add the other variables that we've got in the file, that the things that we think are relevant to making this inference. And then we draw the edges for the direct effects, and you can see where it's important to sort of understand the domain here, right? So for example, the number of years education, right? We can believe that affects their wage. So we say, okay, that affects their wage, draw that line. And in this case, it also affected their eligibility for the program, or their chance of being admitted to the program, so we drew another line there. And in fact, they pretty much came up with this diagram, which shows like a number of variables. And in this case, like age is only affecting wage, but not affecting training program. There was no sort of age-based sort of bias or discrimination there. And then in the tool, you can press the check button. In do-why the library, there's a identify effect function, which kind of does a similar thing. And basically, it will mark up and it will tell you like whether you can actually calculate this effect. It's not always possible, and you can adjust the graph and do different graphs. It may or may not be possible to estimate the effect, but it will mark it up and it will tell you like the approach that it proposes to use for this question. And this is really interesting, right? Because essentially the domain knowledge affects how it's going to generate the model and train the model to answer the question. And there's sometimes like a tendency for people to say, well, let's just control for everything. But in fact, there are certain structures that mean that if you control for too many or the wrong variables, you actually introduce new forms of bias, and it makes your result worse than it would have been without controlling for those variables. You can actually completely eliminate the effect that you're interested in by controlling for too many variables. And so there's a bit of intuition here that there's some scenarios where a confounder variable, you can see the arrows come from that variable and they affect both the treatment and the outcome. In that case, you should control. And a collider is one where this variable is affected by both the treatment and the outcome. And in that case, you shouldn't control for that variable. So all of that's worked out for you. You select a model and you get a result. And that's not quite the end, because there's a bit more sort of about how we can interpret this result and sort of more things that we can do with it as well. So in this case, the result is that the average treatment effect, which is a specific type of estimate, was 1629. In this case, it's saying completing the training course causes participants to earn $1629 more, I think it was per week, or that's a lot of inflation, in 3 years' time than not completing the training. And so because it's like this sort of causal inference that we can do, we can also look at what they call counterfactual outcomes. So that's not what actually happened, but what would have happened under different conditions. And so you can also get those results out of the tool. It says what would have happened if we did something differently. And so first, if we look at the sort of result in the red box there, that is the sort of average wage of the entire group of participants after the 3-year period. So it's 5,300. So that was just actual data. And we can break that down in terms of the actual controls who didn't receive the training program and the actual participants who did receive the training. They were treated. So if they didn't receive the training, their average wage is 4,500, and if they did, it's 6,300, right? So it looks like there's that benefit there. But we can also ask the model, what would have happened if no one had received the training program? And it gives us this result, 4,600. So that kind of makes sense, right? Because that's between, the sort of actual controls value and the sort of average value when half of them were trained. And we can also say, what if everyone received the training? And in this case, the average wage is this higher value, 6,200. So hopefully you can see there that not only are we able to sort of make estimates about what happened, what would happen in similar conditions in the future, but we can also sort of retrospectively change the conditions in which that existed in the data and get accurate estimates of what would have happened and what will happen. Okay, so that was my very quick introduction to sort of this causal space and the talks that we're going to have. I think the key points I'd like to sort of take away is like myself and probably the other speakers are all quite passionate about causality and causal inference, and it's not that we shouldn't be doing all of the ML and AI that everyone else is doing. It's just that we should also be doing more sort of thinking about causality and cause and effect, and sort of explicitly recognising that in the models and experiment designs that we do. And then particularly, like if you work for an organisation where you've got all this data and you've got all this detailed domain knowledge, you can really get a lot of benefit and value out of exploiting that, to provide a causal model and use that to uplift your machine learning models.
Would you say it's an effective intervention?
Well, we'd have to do a study to examine that.
We have historical data.
Yeah, we'll come up with a model tonight. And so there's a huge number of tools out there, and you're just going to get a bit of a glimpse of that tonight. But Causal Wizard is a tool for people who want to do causal inference if they already have a good idea of the model. Thanks. Do we want to do questions now or hand over to the next talk?
Maybe one or two questions. Does anyone have a question?
Sure.
Yeah.
Does it primarily work by, rather than testing what you think is the primary causal agent, is it primarily knocking out what you don't think is other causal effects? Like, is that primarily how it works? Is it basically showing that the other things don't have much causal?
Well, you don't have to just do one experiment, right? Like you've got the same data and you can draw as many graphs as you want, right? So you can actually kind of do those kind of different analyses and look at how different models affect the results. So if you knock out a variable or an edge, you can actually get a bit of an idea, did that affect the result? If you've got a few different versions in mind, there's a sort of also a sense of practicality and expediency, that if you've got too many variables and not that many samples, like your modeling's not going to be that great anyway. So you probably want to sort of keep things on the simple side. I'm kind of getting into more of this idea of like elicitations, like what is a good model, or how do you design a good model? And that is something that these other guys are going to talk about a bit more. But like there's definitely a sort of an element of skill to doing it. But I would think just the initial thing would be just like experiment with a few different models and see how that affects the results. If you've got a good idea of the system, that's probably a good start. Did that actually answer the question?
We have another question over here.
Who built the Causal Wizard app?
Oh yeah, I built the app, but it's based on based on a lot of sort of existing tools that are out there, Python, Django, and and do Y, as I mentioned.
Cool. Well, maybe let's keep the ball rolling. So thank you very much.
Yeah.
Very good.